Writers routinely talk rubbish about rockets. Propulsion systems in science fiction films and TV shows are frequently very badly portrayed. The most common blunder is to assume that spaceships behave like aircraft in space. Rocket engines remain burning until they reach their destination. A spaceship can bank and dive. This is, of course, complete and utter abject nonsense.
The rocket engine began in Imperial China, ironically as an alchemical experiment in search of eternal life. It proved to do the exact opposite. Essentially, the chemical reaction between carbon, sulfur and potassium nitrate produces a large amount of hot gas very quickly. When confined inside a cannon or a gun, the rapid expansion of gas can propel an object at great speed. Reversing the idea, a lightweight metal or bamboo shaft could be propelled through the air using the yet-to-be-discovered third law of motion of Isaac Newton. Rocket propulsion remained this way for another 1,000 years, an unguided, unmanned missile of limited practical value. However, at the end of the 19th century, James Dewar developed a method of producing and storing liquid oxygen, and later liquid hydrogen. Robert Goddard realised that liquid oxygen reacting with a fuel such as petrol would be far more explosive than gunpowder and more practical than cordite. It would propel a rocket with a useful payload in sustained flight. After an initial muddle of design, the modern rocket had been invented. Goddard's peculiar upside-down rockets were intended to be stable in flight. They weren't. He abandoned this idea to use gyroscopes to keep the rocket on course. All the essential elements were there: a vacuum flask for the oxidizer and the fuel, and an electronic guidance system to the gyroscopes to input data which controlled either control vanes or the orientation of the rocket engine. Containing the explosive mixture inside the combustion chamber was as exasperating for Chinese warriors as it was for NASA engineers. Eventually, elaborate copper or nickel alloy designs were used. Ingeniously, one or other of the cryogenic fuels can be used to cool the engine to below the melting point of the metal. Yet, for all the sophistication and brute force, the rocket engine remains spectacularly inefficient. Aware of these difficulties, I designed the Ventura spacecraft from the film Astronaut to only use its rockets as it left the atmosphere. It used a mixture of turbojets and scramjets to eke out the fuel. As Isaac Newton's first law of motion points out, things keep on going unless interfered with. Thus, in space, in vacuum, there's no frictional force from the air to slow things down. Rocket engines need only fire once to start the spacecraft in motion, and then again to slow it down at their destination. Wings, ailerons, and elevators have no effect in space either. Spacecraft orientate themselves using little rocket motors, collectively called a reaction control system. These use hypergolic fuels which ignite spontaneously when they mix. These are usually hydrazine and nitrogen tetroxide, less powerful but less bothersome as they don't need an ignition source.
Films and TV shows that managed to get the details right include 2001, obviously. Apollo 13 took great pains of historical accuracy. However, the writer's sense of lunar geography is decidedly odd. Good luck seeing the Frau-Maro Highlands from the far side of the moon. First Man generally sticks to the science, however, I felt it was quite unfair to Buzz Aldrin. He never said any of that stuff, and if anything was to go wrong with the lunar orbital rendezvous concept, he was the man who could fix it. The Expanse is generally well grounded in reality, although rockets are firing in the wrong direction a few times and the Series 5 was a bit mad. For All Mankind was generally very good, except for the bit with the nuclear rocket engine. Things go very badly wrong in Ad Astra, Gravity, The Silent Sea, and of course that masterclass in bizarre and magical astrophysics, Armageddon. Rocket science, or more precisely orbital mechanics, is simplicity itself. It could be described as how to fall down by missing the ground. If I throw an object, it doesn't travel in a straight line, but in a curve. This is caused by gravity pulling the paper downwards bit by bit. If I hurl the paper further, exactly the same thing happens. It follows a curved trajectory downwards. If I were to blast the paper at phenomenal speed, and if we ignore tiresome things like air resistance and the habit of paper to catch fire, then the same thing happens. The paper falls in a curve. But because the Earth is spherical, the Earth bends out of the way as it falls. If it were to reach a certain speed, roughly 8 kilometers a second, then it would fall perpetually and never reach the ground. It's now in orbit. To go to a higher orbit, just push it a bit further. Although, paradoxically, it will be travelling slower relative to the Earth the higher it goes. At a height of 36,000 kilometres, it will travel around the Earth every 24 hours and appear to be motionless from the ground, geostationary orbit. As Dave Scott ably demonstrated, air resistance can't hinder the eternal fall in vacuum. From the 1940s onwards, science fiction abounds with nuclear-propelled spaceships. 2001: A Space Odyssey uses nuclear thermal propulsion for the Discovery and the Ares moonlander.
This was based on a real rocket engine developed in the 1960s. The underlying concept is surprisingly simple. A fission reactor generates heat. Essentially, this is the controlled disintegration of uranium, which produces neutrons and energy in the form of heat. This is used to expand some sort of lightweight propellant material such as liquid hydrogen or ammonia. As with conventional rocket engines, rapidly expanding fluid squirts out of the engine, pushing the spacecraft along. This type of engine is generally more efficient than chemical rockets, although there are many engineering issues that need to be fixed before this type of engine is practical. A peculiar method of propulsion is the nuclear pulse engine, as seen in the three-body problem. The original idea was to throw a nuclear bomb out of the back every so often, and the explosion drives the spaceship along. This Chindogyu spacecraft is simultaneously very practical and utterly preposterous at the same time. Even more astoundingly, there really was a US project to actually build such a spacecraft. And thankfully, Project Orion was cancelled by the 1963 Partial Test Ban Treaty. There is, however, a serious weak point in this propulsion system. On Earth, a nuclear explosion generates a huge shockwave as the energy of the blast is transferred into the atmosphere. In space, however, the force of the shockwave is limited to the material in the bomb itself, which is fairly minimal despite the colossal outpouring of energy. Project Orion reused the concept of an ablative heat shield. Some of the pusher plate evaporated to shove the spacecraft forward. The TV show fudged two entirely separate ideas together without really thinking it through properly. As science fiction writers pushed outwards to the stars, rocket engines became increasingly inefficient, and so they resorted to more exotic methods of spaceship propulsion. Stay tuned for part 2. May the Force live long and prosper.